today I'm going to talk about whether LLMs and VLMs can faithfully explain themselves. And to first clarify what we're even talking about, we're talking about large language models such as ChatGPT that can get some text input and then can answer to your questions to whatever you have written in text input. And we also talk about vision and language models, or short VLMs, that are language models outfitted with image understanding such that you can input images to them as well, and then they can talk to you about the image as well. So LLMs and VLMs, remember that, because we're when we're asking LLMs or VLMs to explain themselves, they can do so. They can either do so in post hoc, so after they have delivered an answer, they can deliver us an explanation, or they can do so before the answer in chain of thought. So before they deliver the answer, they can say what the reasoning is. So if we ask them nicely to, these LLMs and VLMs can produce these explanations, but the question is whether we should trust those explanations, because there's reason to believe that we shouldn't. LLMs and VLMs as well can endorse users' misconceptions, and they can generate explanations that hide their sensitivity to biasing features in the input. For example, if in few-shot learning, in context learning, we always put the correct answer to be A, then if we ask them about something, they will say it's A, but they will not give the reason that they chose A because A is the most common answer in the examples we have shown there, but it gives some other answers for why it chose A. Also, when we say in the prompt, I think the answer is A, but I'm curious to hear what you think, then the models choose A, but don't say I chose A because you said A, but they say other reasons for what they chose A. And also, on the other side, they can be too insensitive to whatever incorrect labels in in-context learning we show to them, which is a little bit different from what's happening here. And also, they can predict predict answers even when we have irrelevant or misleading prompts in the input. So somehow they're too insensitive to inputs when they answer and they explain things to us, and they're not sensitive enough to inputs, and we never know in which regime we are because these things are actually very different. So what would we like to have is faithful explanations that accurately reflect the true reasoning process of the model. And this is the definition of faithfulness accepted in literature and cited by all papers that are interested in explanation faithfulness. So this is the desideratum. So we would, if we want to produce faithful explanations, we would like to test whether an explanation that was just produced is faithful or unfaithful. So if we have a certain model explanation, and we have some interactions with the model, we have a question, we have an answer, and then we ask it why it has given an answer, and it tells us an explanation. We want to determine whether that explanation is faithful or unfaithful according to this definition. And fortunately, there are already a lot of existing tests for faithfulness in literature, but I'm a little bit unhappy with them, and I will give you the reason why. These tests are either for the post hoc setting or for the chain of thought setting specifically designed, and they work like this. The counterfactual edits test wants to know whether an example instance where we have had an interaction with the model, we have given it a problem where it has to determine whether a premise and the hypothesis are entailed, contradicted, or neutral. And then it also gives us the reason for why it has chosen this answer. And to test whether this explanation is faithful or not, this test does the following. My slides are, for some maybe PowerPoint compatibility reasons, a little bit broken. It shows a test instance where it leaves the problem statement as is, with one exception. It introduces a phrase, an edit, that doesn't actually change the meaning of the problem, yeah, because this is 1 times 2 times 3, which is, not changing the problem. But then if the model changes its answer and doesn't mention this, this phrase in its explanation, then this test deems this explanation unfaithful, which is, a little bit weird, because we are looking at another explanation to test the faithfulness for the actual this explanation. Also, it was applied only to quite old models. T5 is not the most modern language model out there, and also it relies on good input edits. So it determines the faithfulness or unfaithfulness of the model depending on whether it reacts to an input edit or not. And how to find this input edit? Well, the authors train another T5 model to produce these edits such that it elicits a change of answer from the LLM. But we know that LLMs are prone, like all deep neural networks, they're prone to adversarial attacks. And if you just let me try hard enough, I will always find you such an edit that changes the answer prediction and is not mentioned in the explanation, and I can make the model, or I can deem the model as unfaithful as I want to, just if you give me enough tries. So this is what I don't like about this test. There's other tests as well, like constructing input from explanations, where as well it was developed for the NLI setting like this. And we have the problem, we have the prediction, and we have the explanation. And here the test instance takes this explanation and it parses it into, again, a premise and hypothesis. So we take this element and we put it in the premise, we take this element and we put it into the hypothesis. And if the model changes its prediction, but with the reasons that actually led to a different prediction in the first instance, then it's deemed unfaithful. But the problem is that it's very specific to these data sets where these explanations can be parsed very easily because they're very templated, and it works just for the NLI setting, just for the specific data sets, and it was applied not to the most modern LLMs out there. And that it was for the postdoc setting, but for the chain of thought setting, there's, for example, the biasing features test that works for the chain of thought setting. So we have a problem, we have an explanation before the answer, and then we have the final answer. And to test the faithfulness of the model, this test, sorry, the slides are broken again for some reason, they introduce here, I think the answer is A, but let me know what you think. And it deems the LLM unfaithful if this user's opinion changed the model prediction, but is not mentioned in the explanation. And this was applied to Claude 1.0 and GPT 3.5. The difficulty of this test is, again, that you have to check for semantic meaning in the explanation to check whether something was mentioned or not. And the corrupt chain of thought setting is yet another test that was tested for an unspecified 175 billion transformer, which, judging from the author's affiliation, is probably Claude again. And it works like this. You have, again, a chain of thought and a prediction, and it makes a test instance where it introduces a mistake, for example, in the chain of thought. And it deems the LLM unfaithful if it ignores the introduced mistake in the chain of thought and arrives to the same prediction. So these are the rationales of tests for the chain of thought setting and for the postdoc setting, and they've already seen some problems, but to summarize the problems in total for all these tests is that they're either for the postdoc setting or the chain of thought setting, and the postdoc setting test did not test modern LLMs, which is a problem because T5 is not ChatGPT. Then it works. Some tests work only for specific data sets, like, for example, this counterfactual, like this test that was parsing the explanation. It only works where you can easily parse this because of templated data sets. Different papers, and this is the most, the highest quarrel I have with all these tests, is that there are all these tests, but different papers that present all these tests do not apply their tests on the same models and the same data, so there's no comparability whatsoever. And some tests require semantic evaluation of the explanations, which is an unsolved problem, like we don't actually understand the meaning of the explanations with automated systems too well to know whether something was mentioned in the explanation or not. And these tests rely on the semantic evaluation, which is a pity. And also these tests have only binary verdicts. Something is either faithful or unfaithful, but there's nothing like half of faithfulness where, for example, half of the explanation is faithful and half of the explanation is not faithful. And another problem is that these tests rely basically on input edits. So they all create an edited test instance, and they deem the model faithful or unfaithful based on whether the model relies to these input edits or not. But there are models that just do not react to these input edits. For example, GPT-2 doesn't have the understanding of ChatGPT, and therefore you cannot test GPT-2 very well with all these tests. And because they just rely on the following rationale of whether the output changes under an input edit or not, they basically just check whether the LLM is self-consistent in its answer according to an edit, and this is actually not exactly faithfulness, because they do not investigate the inner workings or the decision-making process of the model, and this contradicts the definition of faithfulness that is usually cited by these papers and they all adhere to. And the problem is that the inner workings are indeed important, because answer and explanation generation pathways could differ entirely, or LLMs could even use shared parameters for contradictory answers, and we don't know in which regime we are if we're just looking at outputs under input edits. So self-consistency is all we get, and for some reason the animations are broken, so this is to show that the pathways of answer and explanation could differ entirely, and this shows that they could also overlap, but we never know by just looking at the output. And we accept, I mean, we, as me and my co-authors, accept that self-consistency is all we get so far, and we're honest about it by saying that what people have done so far is not actually faithfulness, like they write in the title, or not faithfulness testing, but self-consistency testing. And it's very hard to get to this actual faithfulness, so we actually just want to make a better self-consistency measure that doesn't have all these shortcomings listed here. And for that, we developed CCSHAP, which is working under the following rationale, that we look at not just outputs, but at how the input contributes, or how the model uses the input when producing the answer, and how the model uses the input when it produces the explanation. And we measure the convergence between this usage for answer and explanation, and that is CCSHAP. So what are we doing is, like, the model is doing a prediction, and we have input contributions that we can get with Shapley values, and we can have the same for explanations, and then for CCSHAP we just compare these two distributions to measure an alignment, because if, or that's our hypothesis, that if the explanation has something to do with the behavior of the model when it was answering, then these input contributions shouldn't be wildly different, they should be just a little bit different. And yeah, this is a simplified version, because the actual way to compute this is a little bit more complicated, because I don't know if you're familiar with Shapley values, but in a nutshell, Shapley values give you feature attributions, or attributions for input tokens for a specific prediction. And when we say prediction, it's not just 6, it's actually the predicted probability or log probability of 6. So let's say here it's 0.2, just for the sake of the visualization. And Shapley values take these 0.2, like it would be a pizza that was, produced from the LLM, and then it slices up this pizza and gives it to the contributors that contributed towards this answer, so to all input tokens. So it takes the 0.2 and it gives some mass, some 0.1 to 3, 0.02 to this factorial, and like if you add all these input contributions up, you get 0.2, except for the 0.1, which is the so-called base value, which measures what happens if there's actually just no input to the model. So the base value is when nobody is playing, what is the outcome of the game? And LLMs have some bias, so they assign, even with no input, they assign sometimes probability to some tokens. So we measure the base value, and then we measure what happens with all possible combinations of input, and then we get all these numbers that when we add them all up, it gets we get 0.2. So those are Shapley values in a nutshell. And here again, the slides are broken. I'm sorry, it always happens with PowerPoint for some reason. Then this is simple to compute Shapley values for predictions that have just one token, but explanations usually are not one token, they're multiple tokens. So we interpret multiple tokens, so we get multiple such input contributions. And also what happens is that, when you interpret a 0.2 probability, your values will be such that if you sum them up, you will get 0.2. But if you interpret a 0.9 probability, your values will be more in the range of 0.9. So they sum up to 0.9. Therefore, what we need to do in order to compare these two things, the first thing is to normalize these values such that they're all between -1 and 1 and not between anything that sums up to whatever the model has said. So we normalize these values, and then, because here on this explanation side we have multiple distributions of input contributions, as many as output tokens we actually have, we also need to aggregate all these distributions into just one distribution. And if the prediction is just one token, we don't need to do here anything. But now we finally got these two input contribution profiles that we can compare, and that's what we use to compute CC-SHAP. And CC-SHAP is this, because we measure the convergence between this with cosine similarity, but it could be correlation, other correlation measures as well. It's a measure between -1 and 1, and -1 means that these profiles are totally opposing. So when this is plus 0.63, this is minus 0.63, and so on, that's -1. And 0 means that there's no correlation, and 1 means that there's perfect alignment between these things, which of course is never the case, but we want the CC-SHAP to be positive to even speak of like aligned and faithful or self-consistent LLMs. So what we have with CC-SHAP, and unlike all previous tests, it's more than a test, because it's not just giving us, yes, it's faithful, or yes, it's self-consistent, or it's not self-consistent. It's giving us a continuous measure between -1 and 1, and that's how we can distinguish between samples in the level of self-consistency. Also, it's interpretable because we have an indication of where exactly answer and explanation use their inputs differently, so we can analyze what the impact of tokens was. It's applicable to both the post hoc and the chain of thought setting, which is the first test to be like that, because before they were developed either for the post hoc or the chain of thought setting. And it's great because it doesn't require the semantic evaluation of explanations, which is an unsolved problem. It doesn't need annotated data like other tests do, because they need to know whether something has changed to the worse or not. And it doesn't require these input edits that are hard to find, or if you find them too good, then that's an adversarial example actually. And it even works for weaker models such as GPT-2 that do not react to input edits, because nowhere in this procedure we have introduced an input edit. So it works very well for GPT-2 as well. And we can get at sample level interpretations like this. So this is this was here for just a toy example to have simple values such that they're humanly understandable. But in real worlds we have such inputs, such explanations, and we can get the profile, the contribution for each token, for the prediction, for the explanation, and CC-SHAP tells us how much they're aligned. And we have this for LLMs, but we can have this for vision and language models as well, where we not only have input contributions for the tokens, and here the input contributions are coded in color. Blue means positive contribution, red means negative contributions, and the stronger the color, the stronger the contribution. But we can also do this for tokens that are image tokens as well, and we plot them here like this. And CC-SHAP tells us how much the prediction side and the explanation side are aligned. And that was at sample level, but at a broader level to measure whether CC-SHAP is good or not, it's not that simple. because we need a comparative consistency bank to know whether CC-SHAP is a good measure or not, because there's actually no ground truth for faithfulness. Remember, faithfulness is all about knowing whether an LLM is following, whether for the explanation the model followed its reasoning processes that it was doing for the answer generation, and we don't know exactly what the reasoning processes are for the model. So there's no grounds that like humans cannot annotate this unless they have understanding of what is going on inside the model. We don't. So there's no ground truth for explanation faithfulness. And existing tests do not compare their tests to each other, so we don't even know whether existing self-consistency tests are self-consistent to each other. So that's the idea of this comparative consistency bank, to know whether existing tests are consistent among themselves. And for that, we need to develop such a benchmark where we basically test 8 existing tests and our CC-SHAP. And we test 11 autoregressive LLMs with it on 5 tasks that we established to be part of this consistency bank. And surprise, surprise, we get a huge table like this, and don't try to focus on each individual number here. What you need to understand from this table is that all numbers are different, because existing tests diverge a lot among each other. So one test for the same LLM says it's 5% faithful, and other tests it says it's 71% faithful, another test says it's 49% faithful, and you can believe what you want, right? But what we find are some trends that RLHF-tuned models get higher self-consistency tests overall. So, but there's no trend between size and self-consistency, because we know that the larger the model, usually the larger the accuracy is. And I know we don't have tested a broad size of a broad range of sizes here, because 70B is kind of the most that we could fit at the in the GPUs at that time. But there is a trend between size and accuracy. The higher the larger the model, the higher the accuracy. But this is not the case with self-consistency. So for the size range that we could test, we couldn't find a relationship between size and self-consistency, but we also didn't totally exclude it. It's like if you go to 340 billion parameters, maybe that changes. Yeah, and what we did for LLMs, we can do for vision and language models as well. So we test, all these tests were implemented for language settings before. We implemented for vision settings as well, and CC-SHAP as well. And we test 3 decoder vision and language models on 6 tasks, like VQA, and multiple choice tasks that this is a challenging task from one of my previous papers. And what we find on VLMs is that they show generally no self-consistency, because LLMs, at least in the RLHF setting, they showed some self-consistency, even though base LLMs didn't, but VLMs just don't. Why? Because the image contributes significantly more to the explanation generation than to the answer generation. So when the model does a prediction, it uses the text, let's say this much, and the image this much, and the text this much, but when it's doing the explanation, it focuses on the image way more. It uses the image way more. And this is a very human-like behavior, if you ask me, because if I ask you how many things are there in the image, you say quickly an answer, but then if I ask you why did you say that, then you start counting very carefully and looking very carefully. And this difference actually is even larger in the chain of thought setting compared to the post-hoc setting, which is also a very interesting finding. So I don't know how time is, but in conclusion, faithfulness tests, or that's what our message is that we have been, or like the research community has been writing faithfulness in their titles all the time, and they say they are measuring faithfulness, but they are actually just self-consistency tests, because they're looking just at whether the model under an input edit is self-consistent or not, but they're not faithful because, or not testing for faithfulness, because they're never looking whether the reasoning process of the model in answer for the answer and for the explanation are aligned or not, because that's not a given for the tests. Also, they work very, very differently. You have seen in those examples that I've shown you for the post-hoc setting or for the chain of thought setting that they have very different rationales. Some rationales are a little bit weird, and especially for this adversarial setting where you try as much as until you find a setting that basically deems the LLM unfaithful. So no wonder that the results are widely different. When you ask a different measure to tell you whether an LLM is faithful or not, they will deliver. They will say for a certain model it's very faithful, and another test it says it's no faithful at all. And especially for GPT-2, this range from some tests saying GPT-2 is 0% faithful to other tests saying it's 100% faithful. So you have as much discrepancy as you can imagine there. Also, they test on different data and models. So before we published this paper, it was not known that they're so different. Now, at least we know. And what we find with CC-Sharp is that instruction and RHF-tuned models have higher self-consistency. So this is maybe a good direction that the models are following when they're doing instruction tuning. They're using the inputs more similarly during answer and explanation generation. And we couldn't find a trend between size and self-consistency, but we also didn't exclude it, so further tests for larger models are needed. And I would say the most interesting part is finding this different behavior in VLMs and how they use the image when they explain versus when they answer. And I think there's interesting directions that one could go into when asking, for example, humans how they do it, like to have a cognitive science test to have humans and somehow measure their behavior when they're explaining and when they're generating and see whether this is aligned to what language models do. And CC-Sharp is still a self-consistency test. We're totally honest about it. We actually just put faithfulness in the title with an or, so it's, we don't actually mean it. It's faithfulness just because we talk about the other people claiming it's faithfulness. What we say, it's still self-consistency, but it's a better step towards this true faithfulness, because we're not looking just at how the outputs differ under some input edit. We're looking at how the model uses the input differently between answer and explanation generation. So this is a little bit more insight into the behavior of the model, but this is not the end of the story, or because more research is needed to actually find the behavior in the inner workings of the model, not just at input level like we did. There's code published for CC-Sharp if you want to use it. There's a paper attached to it. Then in this paper you will also find a reference for the vision and language models paper. So feel free to check this QR code out. And thanks a lot for your attention, and I would love to answer your questions.
Thank you very much for the talk. I have two questions. How CC-Sharp can be applied to LLMs with React framework, where we have reasoning, such that we can also have explanation before the prediction. Will it always give good score? And I didn't get the intuition behind where LLMs, a number of parameters didn't matter on the score, right?
Yeah.
What's the intuition?
Okay, so I'll answer it step by step. The first question is how RAG would be, or how could we analyze the CC-Sharp or RAG framework? Or no?
Yeah, sorry, about that. Reasoning, when we will ask reasoning and then the answer, not the RAG.
You mean the chain of thought?
No, it's not necessarily chain of thought, but similar. So there was this paper, React, where we will ask reasoning and then the prediction itself. So the final stage, for example, when we ask for the solution of one specific mathematical formula, right? We will also get the explanation with the answer as well. So with the React framework. So in this scenario, CC-Sharp will give a good score, right? Because the explanation will be similar.
Well, not necessarily. So this has to be measured and investigated, because I cannot tell you what to expect. But the thing is that, what CC-Sharp does is you say that this is the explanation, this is the answer, and you analyze this answer, and you can see how the input contributes for this answer, and then you have the reasoning part or the explanation part, and then you analyze with Shapley values what the input contributes for this part. So from whatever you got as output, you parse the explanation part, and the answer part, you compute Shapley values for each of those tokens. You aggregate whatever many tokens you have, and then you you compare the contributions profiles, and then you will see whether there's an alignment or not. And it might be that if the explanation or if the answer comes after the explanation, that there's little alignment because the answer doesn't use the input anymore, but it uses or relies just on the reasoning. But that's an interesting research question. Does the model here on this answer rely on the reasoning, or does it rely on the input as well? And yeah, it's an interesting research question. I would guess that the input also matters a bit, especially if you frame the problem as a multiple choice setting, because what I've seen in Norman analysis is that these two tokens, A and B, are very high importance. Why? Because they restrict the solution space a lot. Because if you ask, what is the answer to my question, and then there's free-form answer generation, it could be any token from the vocabulary. It could be cats, dogs, 6. But if you ask, is it A or is it B, then these two tokens from the input restricted to just A or B, so they're very important. Yeah, that's if people ask what is usually in few-shot learning very important, these two tokens are very important because they restrict the solution space a lot, and this explains like what chain of thought even, sorry, not chain of thought, few-shot learning even elicits, because in few-shot learning, as people have found here, the incorrectness of the labels is not even that misleading. Why? I mean, you can give incorrect labels in few-shot learning because actually it's not the meaning of this that's the most important. What's the most important is A or B, because those restrict the solution space a lot. Yeah. So does this answer your first question? And then the second question, could you please remind me what the second was?
About number of parameters.
Number of parameters, yeah. So, just jumping to the slide of the results, because we have had a lot of models in their base version and in their chat version. Almost there. Yes. So the base version and the chat version, and we had different sizes of these models, but you see the range is not great. We have 7 billion, 13 billion for Llama 2, Mistral is just 7 billion and 7 billion. This is 7 billion and 40 billion, and when we plot the accuracy on these tasks, on these samples that we tested, and the size of the model, here always the size here is 7B, but here 13B and 40B, and the accuracy of the model increases, the accuracy of the model or the trend lines increase with the size of the model generally. And of course this is not such a clear plot like you see in other papers because we didn't test so many sizes, but there is clearly a trend, and other papers have found such a trend. But when we plot the same thing, but the self-consistency, CZ-Sharp score on this axis and not the accuracy anymore, we see that there's not clear trend lines. You cannot say, yes, it's surely like this, except for this test, which in this color, for CZ-Sharp chain of thought, there is a trend, but for all the other ones, there's no trend. But we cannot exclude that larger models are not more self-consistent, because we didn't test 340 billion parameters to see whether maybe 340 billion parameter models are very accurate and also very self-consistent. So yeah, it's just that we couldn't exclude a relationship, but we also couldn't confirm a relationship for the range that we tested. Thanks for the questions.
Yeah, thank you very much for the presentation. Very clear, very interesting. My primary question is regarding the discrepancy between the explanation and prediction attributions for the CZ-Sharp values. So that's kind of an interesting result, but what is the intuition for that discrepancy? Is it like maybe number of tokens in the image versus number of tokens in the text? Or?
You mean, how do I explain the differences in C between vision and language models and language models?
No, for the vision language models, but
Yeah.
image versus text. The attribution for image versus text.
Okay.
Well, what's a hypothesis for the reason in that discrepancy?
Yeah, so the discrepancy is harder. So yeah, what we have found is that the image matters a lot more when explaining than in model prediction, because I mean, here we do a renormalization such that you can focus more on what's happening in the image. But if we look at this first row, these are actually, so these values on the text side and on the image side are normalized the same. So you see that here the strengths of the contributions are way less than the strengths of the contributions here, which are higher. So clearly, and this is just one sample, but on the whole data set, we find the same trend that contributions here on the explanation side are stronger in the image than for the model prediction. And it's a little bit like, I don't have the answer why this is the case. The intuition is that it's a human-like behavior where when you need to explain something, you look more carefully. And what we found from previous work is that you ask a question to the model, like how many benches are there in the image, and it says 2. And you're like, why 2? And then you see that 2 is the most common answer in the data set. So during training, to reduce the loss as much as possible without actually understanding something, you predict 2 all the time, because that's, if you see the n-gram how many, that's a giveaway for 2. But the n-gram how many, that's in the text. So text gets a high contribution because how many, here it's not a how many question. I'm just, like this is another, I'm giving a simple example of how many benches are there in the image, how many then is a text. The text n-gram gets a high contribution, and the text and the image doesn't get a high contribution because we know it doesn't actually even look at the image, because you can even delete the image or put a cat video in it and it still says it's 2 benches, yeah? Because models have these problems. Yeah, so you have this problem during answering, but then when you're asking it, you said there are 2 benches, why did you say that? Oh, and then it actually starts to look at how many benches there are. So somehow the prompt here for an explanation elicits the behavior of the model to actually look at the image. And and that's why, you know, let's think step by step, or look carefully into the image, or give yourself some time, let's pause, and prompts like that have been shown also on other cases to elicit better answers from the model. And here it seems to elicit the model that's usually ignoring the image and is just looking at high-level spurious relationships in the text, such as how many, and it's 2. So it's with such a prompt of explaining, like asking the model to explain something, you're eliciting a behavior to actually focus on the image more. Yeah.
Okay, and is it possible, this is maybe a naive question, but is it possible that it's just distributing this value across more of the tokens, irrespective of whether it's an image or text token? Because I'm seeing more highlighted text tokens on the right side as well.
Yeah, so
is that possible?
So one of the reasons why here, I mean, here's also a lot of strong things, but yes, here are more stronger things. But let me show you this image again. The thing with Shapley values is that, you know, if this is large or small, so if this is small, this is small. If this is large, this is large. Or, I mean, if you have a larger pizza, usually the contributors get larger slices of pizza as well. Yeah, so so that's why we need to normalize these values such that we account for these different ranges, and here they are actually normalized, but it's, you know, the number of tokens in this setting and the number of tokens in this setting is the same, because we only count until to the best answer is, that's what we interpret. So it's not like there's here more tokens and here less tokens. So somehow in the comparison, it's really the image usage that is more. And I know that these, I mean, it's kind of difficult to compute the mass of like how much you have here and how much you have here from these plots, because such an A could actually hide a lot of mass, and it's not that visible in the color. I can just tell you that no, it's not the length of of everything that's making things large or small, because the length is the same. And we have normalized the values such that they're all between -1 and 1, and they're not actually differing in magnitude because of large Shapley values when large prediction probabilities occur or small predictions probabilities occur. Yeah.
Okay, thank you very much.
Thank you.
Thank you for the interesting presentation. So I have 2 questions to start off. First with the Shapley value. I know a major drawback of the Shapley value is the multicollinearity, and I can only imagine that within the next 12 data, multicollinearity will be much more prevalent. So do you have an instrument in your mind to tackle this problem?
So just to know that I'm understanding your terminology, with multicollinearity, you mean features that are correlated within the input?
Yeah. So
okay.
basically tokens.
Yeah, tokens. Exactly. So yes, tokens in the text are correlated. Like if you say New York, New and York are correlated. They're more correlated than New York is with is, right? So it's there's a correlation in the text, but there is a correlation in the image as well. So if we have a bench, if we have a bench here, there's probably a bench here, and there's probably a bench here. So I would say the correlations in the image are as bad as the correlations in the text. So I wouldn't necessarily, and one has to measure it because it also depends on the image, how much variation there is in the image. But in this image with a large bench, there's a lot of correlation between these pixels, and background pixels also have a lot of correlations to one another. So what one can do on the image side, and this is not something we have done, is do semantic segmentation of the image, and usually in SHAP computation ablate things together that belong together. That's for the image side. For the text side, it's a similar procedure where one first clusters, or let's say it parses the sentence, and in things that are close together structurally, and they should be usually ablated together or not ablated together at all. So that's a thing that's kind of already, implemented a little bit on the text side, because we have some clustering of embeddings first to do this grouping of text beforehand. But yes, these implementations of making SHAP, like Shapley values, better are a plug and play into our library. And if you just make like a better ablations for the image side and for the text side, you can plug them in, and you can get an updated, better version. But yes, like what we couldn't do in this research is take all problems of SHAP and fix them, because SHAP has problems, definitely. It's just that we didn't want to use any other interpretability option, because they don't have the mathematical properties that Shapley values have. Like here you have additivity, you have that all these input contributions plus the base value, which is what happens, what the output is when nobody here is actually active, they add up to this prediction probability. So these values are meaningful, and they're not like in gradient-based methods where you get 0.1, 0.2, minus 0.3, but you don't know exactly how to, like what the quantity of that is. This has, in physical understanding, a measurement unit, which is the predicted, like this is a fraction of the predicted probability that was done in the end. And because of the mathematical properties of SHAP, we can aggregate things, we can normalize things, which in other interpretability methods is not given. And yeah, we took what's best out there. Of course, it can be improved, and it's plug and play. So if you have better ways of handling image ablations and text ablations, you can just plug them in.
So second question I had was about the interpretability of the negative CC sharp value.
Mm-hmm.
So first of all, does any of the big model have a negative number?
Yes.
Yes. Doesn't it mean that that the tokens are like they are random? Because I'm having a hard time to interpret the negative CC sharp in these contexts.
Yeah. So to answer your question, yes, there are models that elicit negative. So all these red highlighted ones are negative, blue are positive. So there are models that have negative CC sharp. And now to the question of what negative CC sharp actually means, it means, let's simplify the picture in here. It means that these two profiles are opposite. So it's one CC sharp is 1 when this bar is exactly the same magnitude as this bar, which is not the case in this picture, but imagine here it's 0.63 and here it's also 0.63, 0.13, 0.13. That's 1. And we, of course, never get 1 because there is some difference between explaining and answering. It's just that we don't want the prediction to be very different. Yeah? So what we would like is CC sharps of 0.2, 0.3, or the higher the better, but not 1. 1 is not realistic. 0 means that it's random. 0 means that this and this has nothing to do with each other. So there's 0 correlation. And -1 means that if this is 0.63, this is minus 0.63. So that means -1, that if a bar here goes up to a certain degree, it goes down to the same degree in the other direction on the explanation side. So that's what -1 means. So it's a negative correlation. It's when things here are hot, things are cold over here. That's -1. Does this answer your question?
Yeah, I mean, I understand -1 but for example, let's say we have this sample. I love cats; they are beautiful. So let's say when you are trying to explain the same word, has a negative attribution of a specific token.
Yeah.
So how can this be?
How can one token even get a negative attribution? Yeah, that's interesting. So how Shapley values work is that you get your output, your 0.2. And then you delete, you say that these tokens are players that are playing a game, and the outcome of the game is this probability 0.2. And you can say this is Messi, this is Ronaldo, this is another football player, and they're all playing together to get a 0.2. And then to give a fair payout to Messi and Ronaldo in money, according to how much they contributed towards the positive outcome of the game, you want to know how well they played. So it's a little bit impossible if you just from one outcome of the game, but if then you repeat the game and just put Messi on the bench and just let Ronaldo and all the other guys play, then you will see this has changed to the worse. So maybe Messi was very important in that game, and you do this with all possible combinations of ways in which you can ablate tokens. So once you delete 3, then you delete 3 equals, you delete 3 factorial equals, you delete everything, you delete all possible combinations, you record all possible outcomes, and then you see what's the difference when 3 is playing versus when he's not playing. And when the prediction probability with 3 is lower than without 3, then it means that when we don't have the 3, when Messi is on the bench, the outcome of the game is better. So 3 contributed negatively. So that's how you can get a negative contribution, because this token actually was impacting or was making this probability smaller when it was active and higher when it was inactive. That's what it means for a token contribution to be negative. So it's like you have a pizza and you slice it up and give everyone as large of a slice as much they contributed, but somebody has actually ruined the pizza, so they have to pay in pizza, and that's what the negative bar means. Yeah, and tokens, I mean, here, don't take this seriously, because here is just a constructed example by me. Here are actual examples, and you see that there are tokens such as from sentence, there's ends, yeah, so send ends, and ends is getting a high negative contribution, and send is also getting a negative contribution, and these things happen. And you might ask yourself, why is sentence contributing negatively? I cannot give you a human answer because I'm not Llama 213B chat. I cannot tell you. And that's the problem with interpretability measures. We know Shapley values are as faithful as it gets to actually giving us what the model is thinking, but models are not humans. So to me, it looks implausible. Like I'm looking at Llama 213B chat and like, what did you do here? You're weird. But that's what the model did. Well, that's how its output probabilities for B changed when we deleted sentence. And that's what we measure. And yeah, so they may be implausible, but that's what they are.
Thanks a lot.
Thank you.
So thanks a lot for the great talk. Can I please ask you to go to this distribution slide?
To the what?
Distribution slide.
This.
Calculating the
Okay, yeah,
yes.
here. Mm-hmm.
So if I understand it correctly, you are taking this tokens distribution of the, let's for a moment look at the left side, tokens distribution for the question, and then you go and take the tokens distribution of the answer, explanations.
Of the question when the model was answering. Yes.
Yes, like you are taking both the question part, the why part, and then also the explanation part, all the tokens, and then you are trying to aggregate them.
Not exactly. So I'm sorry the slides are broken, but I mean this is exactly the same as this. So this is 3 equals what, and then here's the prompt for asking the question, here's the prompt, here's actually the answer, then the prompt for asking the question, and what we're looking at is, so this is the input, this is the model prediction, and this is what we're interpreting. So we're taking this token and we're looking at this prediction probability, and then we're blaming input tokens for this prediction probability, and that's what we get here. And this is what we do here as well. We have an output token, which, sorry, the slide is broken, but here we have the first output token, and I don't even see what it is, 3. And then we get input contributions for all the inputs, and the inputs here are the question and are the answer, because the answer in post-hoc explanation matters as well, and the prompt for the answer. And we get Shapley values for all of this, but we can just disregard these tokens because they can be, I mean, I've talked about the base value being the outcome of the model when there's no input. Here in this setting, the base value also includes this prompt. So because of the nice mathematical properties of Shapley values, we can just disregard these values and look at this value and this value minus those values, and then we look at this and compare to this.
So like you always look at the same distribution?
Yes.
Just like,
yes.
You do it as many times as many tokens you have for your
Yes, exactly. Yeah. Because in an explanation is longer, so you predict 3, then you predict factorial, you predict equals, and all these things have been predicted because of the certain input that you had, and we blame the input, and you get in autoregressive generation as many input contributions as you have tokens produced, and then in the end we need to aggregate them, because otherwise you cannot compare one distribution to 100 if you have 100 tokens generated.
Yeah, okay, great, I got it. So if we decided to conclude what is C# value 0.1 tokens in comparison, let's say 70 for Facebook from other approaches, like if you go to the result.
Yeah. Yeah, so if 0.1 is large or small, that's what you're asking me?
Actually, like, I'm trying to understand, like, I mean, like, how to understand whether my consistency of faithfulness is
Yeah, so it's hard to say if it's better than 0.3, you're the best. If it's worse than 0.3, you're the worst. That's what I think is the hard question about self-consistency or faithfulness, is that you cannot have like one value where you say faithful or unfaithful, because things are a continuum, things are half a lie, and also this score is based on a heuristic that the answer and the explanation have something to do with each other, but of course there are some different behaviors in explaining and to answering, so this value shouldn't be too high. So I would say if it's above 0.1 it's good from what we see, but I think that better models and testing as many models as possible is the way to answer to this question. Because just by looking at many behaviors, many models, many instances, and when we find an instance with 0.5, then we know that the instance with 0.5 has something special over the instances which have 0.01 or whatever. So it's still an empirical analysis that has to be conducted. And when you see here things like 49%, it just means that from all instances, 49% of them were deemed faithful, but by this hard decision, whether faithful or unfaithful. And here we have continuous values from which we draw the mean. So this is a mean over 100 samples. So there are samples that are larger and smaller.
Like, what's the reason why you didn't have ChatGPT here?
Because they didn't pay me to conduct experiments on it. So the code can be run with ChatGPT as well. Like if you want it, you can pay and run it. I don't want to do OpenAI's analysis. I just chose open models, and anybody interested in Claude or ChatGPT, they can do it. So the code is out there.
Thanks, Letitia. That was an amazing talk. Everyone, let's thank Letitia.